with integration, using symmetry to our advantage can save time. So some ideas. Even functions. Well, we know that's when function negative x is equal to function x. So if we're integrating around 0, we know that going from minus a to a will be the same as going 2 times from 0 to a. That just has the advantage of, well, 0 sometimes is an easier number to substitute in. But here's the thing. If you've shifted the curve, the same idea applies. So that symmetry might be in a different line now. So function x minus c, now we've moved at c, the symmetry is now in the line x equals c. Yeah, sure, it could be a really unusual situation, but you never know. If you notice you're going from c units before and c units after, you've still got that same idea that you could go twice from the c plus a. And same deal with the odd function. The odd functions are nicer, of course, because of the rotational symmetry, and we know the answer is just 0. Maybe this is more useful with the shift. If you've got rotational symmetry about a point, it doesn't have to be the origin, then you know that integral is going to be 0. Now, this one here can be very useful. The integral from 0 to a of function x will actually give you the same answer as the integral from 0 to a of function a minus x. Because if you recall, what does function a minus x produce? Reflection in a on 2. So if you're reflecting in a on 2, well, it's going to be the same area from 0 to a. Here's a proof, other than using the picture. So 0 to a of function a minus x. I'll do a substitution, u equals a minus x. So du is minus dx. Fix up my limits, and I end up with minus the integral of function u du going from a to 0. But I can swap the limits around, and because it's a definite integral, it actually doesn't matter what my pronumeral is. So that would be the same as 0 to a of function x dx. Now, remember this. When you're multiplying functions together, if they're the same type of function, multiplied together, you'll end up with an even function. If they're different type of functions, you'll end up with an odd. So odd times odd's even, odd times even's odd, even times even will be even. That's useful for something like this. Yeah, you could spend some time working out sine cubed and all the techniques, but if you think of sine cubed as sine times sine times sine, and we know sine is an odd function, so odd times odd times odd would give me odd. And so we know that's 0. Square root of x squared root 1 minus x. That's where the reflecting in a on 2 is useful here, because I can turn that square root of 1 minus x into just x. But now I've got something I can expand out and integrate quite easily. So x to the half minus 2x to the 3 on 2 plus x to the 5 on 2, add 1 to the power over the power, sub in, and we have our answer. Now remember, it's 0 to some number, you substitute in that number minus x. So if you already have that number minus x, that's just going to become x. So it gets that as 2 terms into 1 term. So that's why it worked nicely for this particular question. What about improper integrals? So it's a definite integral, but it's where the integrand is actually undefined at some point. So if I said integrate from 0 to 1 of dx on x, obviously that's not defined at x equals 0. So that's our hyperbola. So I change it to be the limit as n approaches 0 of going from n to 1 of dx on x. So that gets me log of x as n approaches 0. So I want what is minus log n as n approaches 0. Well, what's the log of 0? So this one, the integral is still undefined. As opposed to one like this, if you have to find the integral from 1 to infinity of x e to the minus x squared, well again, infinity is an issue, you can't substitute infinity in. That's why in the last one that doesn't work. Okay, so we're doing x e to the minus x squared, which is e to the minus x squared. We get the limit as n approaches infinity of e to the minus n squared minus e to the minus 1. Now that one we can work out. E to the minus n squared, so you've got your backwards exponential if you like. So as n is approaching infinity, that e to the minus n squared will be approaching 0. So therefore the whole thing approaches 1 on 2e. Area and inequalities, and we talked a bit about this with inequalities anyway, but let's have a look at it again. If I know function x is trapped between g of x and h of x, and it's always true going from a to b, then those integrals must also be trapped in the same way. Let's look at an HSC one. So n's positive integer greater than 1. We're looking at y equals 1 on x, and we're going from n minus 1 to n. Well, they've given us that picture. And they've looking at the idea, I guess, of inner rectangles and outer rectangles in their picture. There's the inequality they want us to show. Okay. Well, as I say, they gave me the hint, so I'm going to use it. Inner rectangle will be less than the area under the curve, less than the outer rectangle. So finding those areas, I now have that 1 on n. Integrate the dx on x, we get the log. So log x going from n minus 1 to n. And that'll be less than 1 on n minus 1. Subbing in our limits into the log x, I'll get log of n over n minus 1. Okay, not quite what they want us to prove yet. If I multiply everything by n, I'll get 1 is less than n log, etc., etc. But I'll now bring that power in. So if you have a look at what we're trying to prove, I want n on n minus 1 to the power of n. So I've got that. Now we know e to the power of x is continually increasing. So therefore, I can say e is less than n on n. In other words, I can, is that a word, exponentialize? I can exponentialize all three terms, right? Because it will preserve that increasing nature. And then I'll turn upside down. Remember, with inequalities, if you turn sides upside down, you got to change the integral sign as well. That kind of looks ugly, so I'll write it the other way around. And there it is. So, Old Cambridge, I think I did photocopy that one off, did I? Yeah. Yep, so that's there. 4i from our books, and of course, the 100. But that would be mean setting 100 of them, so you don't have to do number 78.